if it's a growth rate, whoops. If it's a growth rate, then K is positive. If it's a decay rate, then K is negative. And just like in the other cases, growth, it moves away from the asymptote. Decay moves toward the asymptote. Okay. Where are these things used? Well, the most common place that this is used is in carbon dating. You guys know what carbon dating is? It's basically like if you find like a fossil of a living thing, every living things have a certain amount of carbon in them. So if they find fossils of a living thing and they look at the amount of carbon that's been left in there, they can trace it back to exactly how old it is, because they know how much was supposed to be in there, they know how much is in there now, and you can see how long the fossil has been, like fossilized or whatever. Okay. So what they look for is carbon-14. Carbon-14 has what we call a half-life. Okay, so what is a half-life? Suppose you have this much of a material, okay? Suppose the half-life of something is, I'm just going to throw out a number, 5 years. That means when 5 years have passed and you look at this, exactly half of this will have decayed away. When another 5 years have passed, half of the remaining will have decayed away. In another 5 years, half of the remaining. In another 5 years, half of the remaining, and so on and so forth. That is called half-life. It is the amount of, it is the number of years it takes for half of a certain material to decay away. Okay? So, carbon-14 has a half-life of 5,730 years. So, if you had like a bag of carbon-14 in your desk, if you come back 5,730 years later, you would have had exactly half the amount remaining. Okay? Okay. So we need to find the value of K. Okay. So the formula is y equals y naught e to the kt. Okay. Let's write down what we know. Initially, how much carbon-14 would there have been? Why not? Okay? Okay. Now, the final amount is y. 5,730 years later, how much of the y naught remains? Half of it. So final amount is half of the y naught. Okay? So y naught is how much you had initially. 5,730 years later, half of it. So here I say the final amount is half y naught equal to the initial amount y naught e to the k times what's the years? Okay, now y naught goes away. So I have 1/2 equal to e to the power of 5730k. How do I solve this? Take ln of both sides. So I have ln of 1/2 is equal to 5,730k. So k is ln of 1/2 over 5,730. And let's put that in our calculator and see what we get. I get, who's in chemistry now? Have you guys done half-life yet? No. Who's teaching you chemistry? Okay. So in chemistry, okay, so ln, okay, so the way I do it, right, obviously, so I usually do like ln of 0.5. I don't know, it's easier for me to do that. Divided by, how much was it? 5,730, because it's carbon-14. And okay, so I got, e to the -4. You may or may not get it in that. So basically, K is negative 0.000120097. You can, okay. You can do it any way you guys didn't let me finish. So, or it's negative 1.2097 times 10 to the negative 4. Depending on like your operating system and what settings your calculator is on, your answer is going to be given in one or two of these formats. They're both equally fine. So now it says, so that was just the K. So now it says to write the equation for decay for carbon 14. So Y equals Y naught E to the negative 1.2097 what? Times T. Okay? So that's the equation. You've got to have the Y in there as Y. You've got to have the T in there as T. Oh, shoot. Yes, you do. Times T. Okay? Now, why not? You could just leave as why not. We're not given an initial amount to start with. Now here, if a specimen contains 100 grams of carbon 14 today, how much will be left after 200 years? So this is going to be Y of 200 equal to, the initial amount is 100 grams, E to the power of negative 1.2097 times 10 to the negative 14 to the times, how much? 200. So when you plug this in the calculator, make sure you do it in the same way. Don't round, right? So it's going to be 100 times E, times E to the power of the answer times 200. Okay? So it's 97.6097 grams. All right. Questions? Okay. All right. Okay. The half-life of sodium 22. Oh, you know what? Hang on. So look at this. Let's see if this answer makes sense. Okay. You had 100 grams. The half-life is 5,730 years. So 5,730 years after, there will be 50 grams. How much time has passed right now? A measly 200. Barely nothing compared to the half-life. So there hasn't even been enough time for this to decay. So does it make sense that from 100 grams, we're only down to 97.6? Yes. You see that? So always think about whether these things make sense. Okay, these are so much fun. The half-life of sodium 22 is 2.6 years. Oh, and by the way, like when it has like carbon-14, sodium-22, these are different isotopes of the, right? Have you guys learned about isotopes? They're different isotopes. So it's like the same number of electrons and protons, but different neutrons, right? So like these are the ones that are more radioactive and they decay. Okay, they're more unstable, right? Okay, so half-life of sodium 22 is 2.6 years. So that's a quick turnaround. Okay, determine the value of K and the equation of decay. So it's the same exact thing. Y equals Y naught e to the KT. But this time we could be more quick about it because we know the final amount is half Y naught equal to Y naught e to the K times 2.6. It's always going to be like this. The Y naughts cancel. Half equals E to the 2.6K. ln of both sides. ln of a half is 2.6K. So K is ln of a half over 2.6. So ln of a half over 2.6 is this, negative 0.26660, right? Okay. Does it make sense that K is negative? Why? Because it's decay, it's a negative. Very good. Okay, good. So y equals y naught e to the negative 0.26660t. Yes. So much fun. I love this. Okay. In chemistry, usually they start from here or from here. Right? Like you don't start from there. Anyway, whatever. Okay, a geologist examining a meteorite estimates that it contains about 10% as much sodium-22 as it would have when it reached Earth's surface. How long ago did the meteorite reach Earth? Okay, so y equals y naught e to the kt. Okay, y is the final amount. It has 10% of the initial amount. So if initially it had y naught, right now it's got 0.1 y naught when initially it had y naught. E to the negative 0.26660 t. Y naughts go away, right? So 0.1 equals e to the negative 0.2, you know, that number, t. Okay, so, right now it has 10%, right? Originally, it had the full amount. So the initial amount was y naught. That was the initial amount. Right now, it has 10% of this. 10% of y naught is 0.1 y naught. Okay, so ln of both sides, ln. So ln of 0.1 equals this number. I could do these all day. Wait, I do these all day. How fun is that? I'm going to do it again last period for G period. So much fun. Okay, so what's T then? Right, 0.1. Okay, so how much is that? You didn't round, right? Huh? Like initially. Good. Good. Because we don't round in the middle. Okay, so what do we get? 8 point, is that what you got? 8.6370. So it's about 8.6 years. Okay, does that make sense? It's 2.6 years, right? So in the first 2.6 years, there's 50% remaining, you know, and another 2.6 years, there is like 25% remaining. And so it makes sense that in like 2-3 cycles in 8 point whatever years, this is how much we have. Okay? All right. Okay, so when you are talking about half-life, right? When we're talking about half-life, we know that this is a continuously decaying function. You don't have to see the word continuous explicitly given to you, all right? Because you have something analogous, half-life, okay? So here, the population, okay, so in 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion. So it says determine the K value for China's population growth and the equation of growth. Let's pause here for a minute because I need to talk about like semantics a little bit. When it's talking about the K value, again, it's assumed that this is continuous rate because K is for continuous rate, R is for not continuous, okay? Otherwise, it would tell you find the rate of continuous growth, and you know how to do y equals y naught e to the kt, okay? Okay. So initial is 1.32, and then it went down to 1.26. So 1.32 is equal to 1.26 e to the k times, how many years is that? 7. Okay. So 1.32 over 1.26 is equal to e to the 7k. ln of 1.32 over 1.26 is equal to 7k. So k is ln of this over 7. Can somebody tell me what k is? How much? 0. Wait, I have something else. Yes. Huh? Okay, would it be negative or positive? So in 2000, this is the initial amount, 1.26, and then it grew, so good. Okay, so positive. So when is it going to reach 1.5 billion? 1.5 is equal to 1.26 e to the positive 0.006645 t. It really doesn't matter. If it hasn't specified, it doesn't matter, but go until you have at least 4 like non-zero digits, because in here you're going to use the unrounded answer anyway, right? Yeah. Correct. You don't have to write out the whole number. It's because it all cancels out. The trouble I run into all the time, I want to say about like 30 to 40% of students, if I wasn't asking you for the time, if I was asking you, let's say, you know, in this many years, what's the population going to be? People will say like 136 instead of saying 136 million, you know, and that's that's a big error. Okay, so 1.5 over 1.26 equals this. So t eventually is going to be what? ln of 1.5 over 1.26 over 0.006645. So that's 26.2 years. And when it says when and you have the years given, it's good to say like the actual year. So it's in 2026. Okay? What's China's population now?
Is this like true or is this just written?
No, it's usually true because I get them like from the book and they have like cited sources and stuff.